Hey folks, this is Elliot here, and this is my first video in a series of going over some fundamental mechanisms of physiology. This is a piece I wrote on carbon dioxide and its interactions and effects on both the mind and the body. And I just wanted to read this bit here, which is: the Bohr effect enables the body to adapt to changing conditions and makes it possible to supply extra oxygen to tissues that need it the most. For example, when muscles are undergoing strenuous activity, they require large amounts of oxygen to conduct cellular respiration, which generates CO2. These waste products lower the pH of the blood, which increases oxygen delivery to the active muscles. Okay, so what is the Bohr effect? The Bohr effect describes the decrease in oxygen affinity of hemoglobin in the presence of low pH or high CO2. So both the pH and CO2 have an effect on hemoglobin, and they basically, this is stabilized, but they hold hemoglobin in a structure that allows oxygen to more easily depart and then enter tissues that are around it, so wherever the blood is at that time. I think it's a very elegant physiological solution to delivering blood essentially where it's most needed, because oxygen will be most readily released where the partial pressure of CO2 is the highest. So if you think about breathing in oxygen in your lungs, and there's a fairly high concentration of oxygen right there, and it wouldn't serve if all of it was just return off gas. So it travels into the system at a relatively low partial pressure of CO2 and goes to places which are the most metabolically active, also having the highest partial pressure of carbon dioxide. Whether that's the muscles or the brain or the guts, it's a very elegant, emergent, if you will, way for the system to deliver oxygen to cells where it's needed. Okay, so here are Bohr's research curves. On the left, we have the oxyhemoglobin, the percent of oxygen on hemoglobin, and on the x-axis, or the bottom, we have the partial pressure of oxygen in millimeters mercury. And then we have z-axis, which is the different curves. And what it's trying to show is that at a low concentration of carbon dioxide, in this case 5 millimeters mercury, you have a very high affinity for oxygen on the hemoglobin, even at a very low, relatively low pressure of oxygen. And then, if let's say we kept the same pressure of oxygen and we increased our CO2 to 20 millimeters of mercury, then we have we've changed our affinity by, I think, more than 20, right? So this is, let's call this 85 right down here, and this is 65. So we've gone 15 millimeters of carbon dioxide, and we've changed our affinity by 20 millimeters on that hemoglobin. That's a percentage, sorry, so by 20%. You can see that as your carbon dioxide percentage goes up, your affinity for oxygen goes quite a bit down. And the normal, this 40 right here, is what we would think of as a normal physiological range of carbon dioxide. Although it's probably safe to assume that in modern society, people are moving closer and closer to 20. Okay, so why is the Bohr effect important? If I haven't made it clear yet, it's important because the Bohr effect makes clear the importance of carbon dioxide for the delivery of oxygen to tissues. And so it's not simply breathing more that gets us more oxygen. We actually need to consider a range of other factors for how our cells are going to get the oxygen they need. All right, so beyond the Bohr effect, we have the fact that the ratios of oxygen and carbon dioxide also affect the release of nitric oxide. And that, in turn, affects the vasodilation or constriction of the same blood vessels. So when you have more carbon dioxide, the tissues release more nitric oxide and they vasodilate. So let's just point that out here. In this study, carbon dioxide influence from, let's see what year, 2011, carbon dioxide influence on nitric oxide production in endothelial cells and astrocytes. So the thing I want to just point out here is that nitric oxide production is increased during this is increased carbon dioxide, and then nitric oxide is decreased during hypocapnia. This is reduced carbon dioxide, regardless of pH. So you increase carbon dioxide, increased NO, increased vasodilation, increased blood flow. So when you have extra carbon dioxide, you get more blood flow from bigger tubes, bigger pipes in the vasculature, and you get easier oxygen dissociation from hemoglobin. And that's just all part of this elegant system for delivering oxygen where it's needed. And how do we know? How is carbon dioxide a signal of where oxygen needs to go? Essentially, carbon dioxide is the output of oxidative metabolism. So the basic, not to get into the Krebs cycle, but the basic condensed formula is something we could all know, which is you breathe O2 and your body makes or eats food and then makes glucose mostly, and those two together become water, H2O, and carbon dioxide. So anywhere there's metabolic activity from oxidative metabolism, you're getting CO2. So if the cells are using their energy through some kind of activity, then they are putting off CO2, which is causing local vasodilation and recruiting oxygen to the scene. All right, so we looked at those curves, but we can look at this paper from, I think, what year is this? I don't know. It's 80s. I think it's 84, 85. What journal? I don't really know. But the title of this is Hyperventilation Syndrome, a Diagnosis Begging for Recognition. And this is an argument which has been entirely ignored by psychiatry and the pharmaceutical industry because it would not serve their purposes. But essentially, the authors are trying to make the argument that when you hyperventilate, you off-gas CO2, and that is basically the main cause for all kinds of psychic distress. And what I wanted to really take from this was the massive change in blood flow delivery from a relatively small change in partial pressure of carbon dioxide. So if carbon dioxide is retained a little bit, so each millimeter of mercury, which is really just a way of describing the concentration, then there's a 2% increase in cerebral blood flow. And what we need to know is how much does the CO2 change for certain different states. If we're breathing fast in a hyperventilatory state, how much will our blood flow change? So I found this paper describing that. They're doing it with a ventilator. So acute hyperventilation increases the central venous to arterial partial pressure of carbon dioxide difference in stable septic shock patients. So what they've done is they've put these patients on ventilators and they're monitoring their change in concentration of carbon dioxide. So they went from starting points of an average of 44.5 to an average of 34 over the population. So we're looking at about 11 and a half millimeters of mercury. So in these folks, they would, if that 2% holds, they would have lost something 22 to 23% of their cerebral blood flow would have been constricted away. And that doesn't even, so that's a smaller number than the actual amount of oxygen delivery. So they're losing 22% of the volume, and then they're losing an even greater, but at least in this paper, and I haven't done the math, but they're losing a whole other amount of oxygen delivery from this change of the affinity of the hemoglobin. So they lose 22%, and then let's say, what does a difference of 10 get us? I don't know what their oxygen pressure would be, so we would have to figure that out. But let's assume that they'd be over here. I don't know. So I can't really say. I have to do more work to figure out what the percentage loss of oxygen delivery would be based on the difference in both volume of blood and the change in affinity. But anyway, needless to say, it's going to be greater than 23%. So you could lose 20 to 40% of your blood flow or your oxygen delivery to your brain just by hyperventilating a little bit. A side note, a relevant note, is that this kind of thing, this change of oxygen delivery, is part of the reason that in the early days of COVID, if not the main reason, that in the early days of COVID, hospitals were killing their patients. They were basically giving them forced oxygen while actually depriving their cells of that very same thing. Okay, and this is just, again, another reference for the norm of carbon dioxide concentration in the blood, somewhere between 38 and 42. And then I have another paper here that's just talking about how these researchers induced panic in their patients. The way they would induce panic is to do one of three things. They would increase lactate, they would do a single very high concentration CO2 inhalation, or they would have them hyperventilate. So it's known that you can induce panic from hyperventilation, and I thought it was also curious that you can infuse lactate, which is the byproduct of non-oxidative metabolism. So both of these are, so basically this is a lower pH plus a signal of very inefficient metabolism, and that induces panic. Okay, and then here's another paper describing what a relatively normal, this is saying they're using that lactic acid test to induce panic, and they're finding out that if you actually have a normal, what they're saying normal percent CO2 in your blood, then you're actually relatively immune to that panic. However, if you have a lower than 40 concentration, then you're susceptible. It's just something that is consistent with the same story. And here is Patrick McEwen, who teed up that one of these studies, but also built a whole brand around slow, shallow breathing to reduce the oxygen concentration, increase the carbon dioxide concentration, and allow more oxygen delivery to the cells. And so I wanted to just capture him talking about this change in peripheral blood and oxygen delivery.
Gary, in 1984, in a paper called Hyperventilation, a diagnosis begging for recognition, said that every 1 millimeter drop of CO2 reduces blood flow to the brain by 2%. We also know from other papers that 30 seconds of hard breathing can lower arterial CO2 from normal of 40 millimeter of mercury pressure down to 20. Well, if there's a 20 millimeter drop of arterial CO2, it translates into a 40% reduction of blood flow to the brain, and that's as a result of 30 seconds of hard breathing.
All right, so he's trying to make the point that you can lose even more than what I was suggesting in blood volume. So that's only 30 seconds of hyperventilation. And I guess if you or anybody experienced panic attacks, they don't just last 30 seconds. So they're probably off-gassing even more carbon dioxide, probably down into the sub-20, 10 millimeters of mercury range. So I wanted to finish this up with come into play. Adrenaline, when it's released, evokes a higher sensitivity to carbon dioxide. So one thing I haven't mentioned yet is we naturally breathe to our set chemoreceptors for carbon dioxide. So we will breathe faster to the extent that we are more sensitive to carbon dioxide or to the pH in our blood. And hormones, like stress hormones, will change that receptor sensitivity. I don't have a full list of those things that will increase our sensitivity, but it's something for me to dive into. But you can just use your intuition that essentially if your mind is producing adrenaline or cortisol, and it will intelligently make your body increase the sensitivity so that you breathe more. And that is in preparation for some kind of physical or, I guess, cognitively challenging event. But if that physical event doesn't occur, then you've just put yourself in a hyperventilated state, and you're going to feel very anxious. So what we think of as psychiatric problems are deeply related to metabolism. And before I finish this relatively quick video, I just wanted to say that I found this little tidbit interesting as I've been messing around with alkali metals and looking deeply into those. I found that, so we just saw that adrenaline increases sensitivity to carbon dioxide, and turns out that lithium blocks adrenaline. It's giving a bit of the story for how lithium works in bipolar disorder, and it's doing that by reducing epinephrine, which is adrenaline. If you wanted to reduce your own sensitivity to carbon dioxide and breathe more shallowly, you could just take some lithium, amongst other things. And that's all I've got for you. Thank you very much.